Okay, so in DX11, the way the tessellation was added is that there were two new shaders added to the pipeline, the hull shader and the domain shader, and they have very distinct roles. In general, what happens as content comes in is the vertex shader is used to animate the character. It animates the control points of the surface or the vertices of the triangles that are going to be tessellated. And then the hull shader takes that representation. If you think of end patches, an end patch is basically a surface that's defined by a triangle with the normals at the corners, which is a very convenient thing because there's a lot of content out there that already exists that has that representation. So what the hull shader does is it takes a triangle with normals in the corners and it converts it into a representation that the GPU can evaluate efficiently. Because it turns out that the way that the GPU does that evaluation is by evaluating a polynomial, by a bicubic polynomial. I've spent most of my life working on that kind of stuff, so later on you guys want to talk about stuff like that, I'm happy to chat about it. But basically what the hull shader is doing is it's converting it into a representation that we can evaluate, and it's also computing the level of detail that we want to use when we dice that thing up. So based on how far away the object is, its orientation with respect to the camera, its importance in the scene, what displacement maps are being applied and so forth, you compute how many triangles to break that thing up into. That level of detail is passed to the tessellator, which then generates both the topological information describing the mesh and the parametric values that describe the locations of the vertices in the mesh. Those parametric values are passed into the domain shader, and each shader in the domain shader evaluates a point on the surface and any of the other attributes that are necessary. That computed mesh is then handed off to primitive assembly, then handed off to the geometry shader, as in DX10. And Jonah said, well, you couldn't, in previous APIs, you couldn't generate geometry on die. It's not strictly true, just to be accurate. The geometry shader could do that, but it had very limited functionality. And in fact, the genesis of the geometry shader was that it should play the role of doing, in effect, post-processing from the tessellator. And there's a bunch of history as to why it showed up before the tessellator. But in any case, the pipeline is now complete. You do animation, you do tessellation, you do some post-processing like generate stencil shadow volumes or render cube maps, and the geometry shader, and then you basically sort of finish this rendering pipeline. Any questions about this? Yes?
Domain shader, I mentioned that domain shader evaluates the points on the surface.
Yes.
Evaluates it in what way? I don't understand.
It's a great question. So the input to the domain shader is the control points, the things that describe this surface. It's a representation that's easy to evaluate. But the other inputs that come from the domain shader, each thread gets parametric coordinates of the point on the surface. Now it's up to the developer to decide how they want to represent the surface. The example that I had was it's a bicubic surface. So you plug these parametric values, the u and the v, into this bicubic equation, and out pops a position in space. You could as easily have a domain shader that evaluates the equation of a cylinder. So the UV values are like theta and phi, or it'd be theta for going around and then the height on the cylinder. So you could draw a column with probably, what would you need? You'd need a point and an orientation that says the vertical extent of the column and a radius. And then you'd be evaluating sines and cosines. Work great with sines and cosines. But I think the point that you bring up, which I didn't stress enough, is that there are no assumptions in the API about how the surface is represented. The only thing about the API, the only thing that API stipulates is that it's some kind of parametric representation, which means a pair of parametric coordinates come in, a u and a v, And you use that to decide how to evaluate the thing. So, anything else? Okay. All right, so what can you do with this? So here is a picture of water. And we've been working on water off and on for an awfully long time. It's hard to render water. And it's hard because people know what water looks like. It's like, it's the same problem you have if you're trying to render human characters. Human characters are tough to render because you all know what they look like. And it's no accident that most games, particularly years ago, had zombies or aliens from outer space. It's because we don't, well, zombies just don't look good anyway. But, aliens, I don't know what they look like. So I don't have any preconceived notions. There's no need for suspension of disbelief. So, water. And actually we're going to go to a demo in a moment. But another use of tessellation, which is a little bit less obvious because this isn't a surface, is hair. Okay? The tessellator has a mode that, in addition to being able to draw triangles, it can also draw lines. In sort of mathematical terms, these are called isoparametric lines, and all that means is it's a line on the surface that has a constant parameter. One of the parameters is constant. So you get this family of lines across the surface. And what the tessellator does is it produces a huge number of sort of line strips, connected lines, curves on the surface. And then the geometry shader takes those lines and converts them into triangles that have some finite width so that the hair actually has width in screen space. And then that is, and actually another piece of this that we'll talk more about kind of in the back end of this presentation is compute is also brought to bear in this environment to do the physics of hair, to model the interaction between the hair and this post and these cylindrical shoulders, but also responding to wind, other characteristics. So I think with that we should all get up and switch to the demo and have a look at this stuff.
So, Henry, do you want to talk to this?